Thank you. My name is Julia Lawall. I'm a researcher at Inria in Paris. My main interaction with Jens was quite a long time ago, actually. It's surprising how fast the time has gone. So in the mid-1990s, we were both postdocs in Boston, and I have also had the chance to discuss with him at various times in the future. And so this talk is sort of about how he has contributed to my view of research. So yes, in the beginning, I was a postdoc at Brandeis, and Jens was a postdoc at Northeastern. And at that time, the thing to do if you were interested in programming languages in the Boston area was to attend I think it was every Wednesday, the seminar at Northeastern that was organized by Mitch Wand, where we had the presentation of a paper, and we afterwards enjoyed a discussion and some food. There was like some Middle Eastern food truck. I enjoyed baba ganoush, not exactly in this format, but it was the best picture I could find. At the time, Jens was working on this paper that impressed me a great deal about the type system equivalent to flow analysis. I very much appreciated the idea of thinking about something. I mean, we've got these two things, type systems and flow analysis. We kind of familiar with them, take for granted how they are, but it seemed like an interesting idea to think about them deeply and try to understand what the connections were between them. So moving forward, a little bit of time went by. Actually, Jens went back to Denmark for a little while. And then a bit after that, I left Boston for a postdoc in Rennes. Coincidentally, Jens came back at the same time, and as I left, and I dumped my apartment and all my furniture on.
We still have some of it in the house.
Okay.
Most of each.
Okay, that's good. Some of it was nice, some of it was not so nice. I mean,
some of it was very nice.
It was grad student furniture collected from other people's yard sales, but some of it was nice. Anyway, so I was a postdoc in Rennes in France working on partial evaluation. I'll talk a little bit about partial evaluation now. Partial evaluation is something that it's a program transformation approach. It aims to fully automatically optimize some source code with respect to some of its inputs. So in a very brief example, this is quite a classical example. We have an interpreter for an expression, takes expression and environment, and then it just figures out what to do for additions and figures out what to do for variable references. And so if we want to evaluate this interpreter, we evaluate the interpreter with respect to some appropriate arguments. We have an addition expression. It has a variable x and a variable y. And then we also have an environment. This is mapping those variables to their values. So this is all written in Scheme. Scheme is actually a language I have not used in the last 20 years, but it's quite funny. I actually had to ask my PhD student to translate some ML code into Scheme using ChatGPT to generate this. But it's in Scheme because partial evaluation at the time was quite focused on Scheme. Scheme is a language that's easy to manipulate, easy to generate code that can be executed, and so on. So basically, here our idea is we're going to evaluate this expression with respect to this environment. We start out with our add. We see add here. Now we need to sum up the interpretation of those two sub-expressions. Now we have var x, which will be one of our expressions. A soak is the Scheme way of looking around in a list to finding the value that's associated with a key. And so we'll find the value 3, we'll find the value 4 here, and then we'll add them together, and we'll get 7 as the result. So not very surprising. That's normal evaluation. Then we have partial evaluation. Partial evaluation is kind of the same thing, but we don't have all the inputs. So the idea is you have only part of the inputs, and you try to optimize fully automatically the program as much as you can based on the information you have available. So the typical case is we partial evaluate an interpreter. We have an expression, and then we don't have our environment. We just have a representation that indicates what information we have. It's this called static, and so we have a S for the first argument, and D, this is the unknown thing, indicating that the environment is not known. And so then it's kind of like evaluation. We just kind of do our evaluation stuff, but we just stop when we don't know what to do next. So here we're doing partial evaluation of our interpreter. We have add expression, and so now we have enough information to be able to simplify the add expression And so we can figure out that we need to work on this. And now we will work on var x as E1 and var y as E2. And we have the same, actually the same pattern of execution as we had in our original call. We have our expression, we don't have our environment, and so we can try to push things forward with respect to that information. For example, for var x, we will come down here. Now this x is the string x. And then the evaluation is going to be to try to do this assoc. But assoc requires looking around in the environment, and since we don't have the environment, we obviously can't do that. And so now this is where we're different from evaluation. We have to actually reconstruct the term. So we'll reconstruct this assoc xenv, we'll reconstruct assoc yenv as the result of this interp here. Now we have addition. It's got two arguments. We don't know what they are either, so we need to reconstruct that. And so we produce this specialized program that is in principle much faster than the original one and has fully taken advantage of our addition expression, and it just left over the things that depend on the environment. So this seems very nice. It looks like it did something. So this is something that was studied quite a bit in the University of Copenhagen and also in the team in Rennes that I joined. Basically giving partial information about a function's inputs, partial evaluation is going to fully automatically produce a function that's specialized to these inputs. On the other hand, people using this kind of found some difficulties. One of them is that this whole process requires access to the full source code. This is a source-to-source transformation. We're analyzing the source code. We need the source code to do something with that. But if you think about scaling up to real applications, for example, are going to have libraries. We don't necessarily have the access to the source code. So then what do we do in that case? And the other big problem that came up is that we have this known information and the unknown information, and sometimes some computations can involve mixing the unknown and known information, and then we don't really know what to do next. So we already saw that in the case of assoc. That was kind of expected, but in many other applications it was found that the propagation of your known information could get blocked by some interactions with the unknown information. So this sparked an entire industry of doing what were called binding time improvements, figuring out how to kind of isolate all the known information and keep it separated from the unknown information. One would have to, it was supposed to be a fully automatic transformation, but one would have to do a lot of preparation of the source code to get that fully automation to work out. So partial evaluation had been going on for a certain amount of time. And in 1998 in the University of Copenhagen, there was a summer school on partial evaluation practice in theory. And I attended that, and Jens attended that also. And at some point, for some reason, we had the occasion to walk around these very nice lakes that are around the center of Copenhagen and kind of chat about the future of partial evaluation and where this was all was going and so on. So basically, the concern was how can partial evaluation make the jump from the toy example, like I showed, to doing something applicable in practice. And so there was kind of a first step in this direction that was made both at the University of Copenhagen and at the team that I was working with in Rennes, which is to do, instead of doing partial evaluation of scheme, to do partial evaluation of C. So there's a CMix at DIKU in Copenhagen and Tempo in our team. But this was kind of, if you build it, they will come or something. It wasn't really clear what was going to happen after actually developing these tools. And we come back to these issues that I highlighted before. We still need this full source code. As we're all familiar with, C code has lots more library uses. malloc, you don't want to know what's going on under there. So the partial evaluator cannot be analyzing the implementation of malloc, but on the other hand, it has to know what to do when it comes to a malloc or printf or sign or any kinds of library functions. Some of them it should be unfolding if it knows all the information, and some of it should not because they have some kind of side effects that needs to be preserved for the specialized program. So in Rennes, in Tempo, they came up with some kind of interface file where they have some kind of simplified definition of these kinds of library functions. I remember Jens thinking that was kind of a good idea. One could think about what kind of analysis you could do with respect to these interfaces and so on. And of course, there was also this issue of binding time improvements. In Rennes, there was something called specialization classes, where we tried to think about like good patterns of specialization programs that would work well with partial evaluation, and then developers could perhaps take those patterns and compare them to their own source code and see if they could do something. So there were different efforts to try to improve the situation, try to bridge this gap. But over some time, I think the level of enthusiasm kind of dimmed a little bit. And I think, at least from my point of view, or from the point of view of some of the people around me, the problem seemed to be this idea of full automation. Automation is the idea of you're supposed to give the partial evaluator a couple values, and it's supposed to do miracles in improving even maybe the complexity of your program. So all this full automation is alluring, but in practice, maybe predictability is the key to usability. If your developers are really going to use their tool, they have to somehow know what to expect. And so the rest of this talk is actually not related to Jens in any way, but it's sort of informed based on this discussion that we had in Copenhagen, different interactions, with this goal of how can we do interesting things with programming, program transformation, programming language concepts that will actually have some impact on real developers. So in 2004, I was on sabbatical in France. I worked with Gilles Muller, who also actually had invested a lot in partial evaluation, in actually trying to apply it on real code, sometimes with good results, but good results after a huge amount of perhaps difficult effort. And so the problem that we targeted was, how can we maintain software at a large scale? So for some kinds of software development problems, the developers know what they want to do. They know what kind of code they want to change. They know what kind of changes they want to make. And all they need is help in navigating all the code and making those changes in a reliable, comprehensive sort of way. So we focused on the Linux kernel. Linux kernel at the time we started was 4 million lines of code. Today it's 26 million lines, almost 26 million lines of code. It's still rapidly growing. It also incurs frequent changes to improve performance and to prove correctness, fix bugs, provide new features, and so on. It's kind of an endless problem to keep it up to date. And so the question then is how to perform evolutions in such a large code base. And so in thinking about it, we tried to, well, I mean, our goal was somehow to provide something that was like sound and meaningful and would do proper things, but also something that would be accessible to the developers that we were targeting, who we hoped would actually use the tool that we were considering to develop, and use it enjoyably, not with great deals of frustration. So an insight was that somehow patches are the key to reasoning about change in the context of the Linux kernel. So a patch is just a description. It's just a small fragment of code. We're going to remove, it has just a few annotations. We'd like to remove some lines. We'd like to add some lines. It's a very simple concept. It can be created automatically if you have the old version and the new version. It's the way that developers communicate about their changes. Somebody is making some change. Maybe they would like feedback from someone else, some kind of code review. They can send the patch. The other person can see how things were before, how they're going to be now. And so then they can make a proper assessment of what's going on. On the other hand, patches are not very good for what our ultimate goal was, which was to be able to make changes at large scale, because a patch is going to specify, I cut it off here, but it specifies exactly what file is going to be affected. It's going to specify exactly what line numbers are going to be affected. It specifies some neighboring lines. It has some variable names here and stuff like that that might not actually be relevant to what we want to do. So the patch idea is good from, coming towards the competences of the developer, but it's not really good for doing things at a very large scale. So just to comment on what we're trying to do here, this kmalloc is the Linux kernel's internal memory allocation function. memset is just like it is at user level. We have a region of memory where I want to put zeros everywhere. So the idea here is that we allocate some memory and then we zero it. And this is 2 lines of code when we could just write it in 1 line. because there's this magic function called KZLEC that will do both of those things at once. So it's a very simple change. We just want to change one letter here from M to Z, and we just want to remove this line. It's like 20 keystrokes or something like that. But this is actually quite a hard thing to do at scale, because there are actually many calls to KMELEC, and they're not actually all next to memsets. There are many calls to memset. They're not actually all next to KMELECs. And the distance between them here, it's about 5 lines, but it could be larger or smaller distance, and so on. So it's hard to actually scan your code base and find all the opportunities. So basically, our idea was to take these patches that everybody's familiar with and somehow raise the level of abstraction. So what we do is basically we introduce meta variables that are going to represent any arbitrary expression. And so that's here, this transformation doesn't really depend on what these two values are, so we can just put some random meta variable there. On the other hand, the transformation does require this to be a 0, so then we can put a real value. So we can just freely mix the things that look like ordinary source code and things that make the transformation more abstract. We also have this ... operator. It's like, the idea is like if you're talking with your colleague, you want to describe what you should do, maybe you're at lunch, you write it on a napkin. This is supposed to be something that's like what you would write. And so you can take this rule and then you can apply it across the Linux kernel, and then you get rid of all your KMELECs and memsets and turn them into KZLECs, and then your code is a little bit shorter. So this, we published the original idea in 2008 at Eurosys at a systems conference, because we're targeting Linux kernel. But on the other hand, we are somehow designing a new programming language, and all these operators and meta variables and everything, they actually have a precise semantics that we actually hope our users don't think terribly much about. We kind of hope that this chosen semantics is what they expect it should mean. Maybe that doesn't work 100% of the time. But we worked out all the semantics, and so that led to a paper at POPL. And then here's a retrospective paper that kind of reflects on the lessons learned about 10 years later. So we can go back, we can look at our tool in terms of the 2 criteria, automation and predictability. So we've definitely sacrificed in terms of automation. We don't just like say, I do this, it just should happen all by itself. You have to actually script everything you want to do. Sometimes there are multiple cases that you need to take into account, and you need to actually script all those different cases. On the other hand, the actual transformation part is fully automatic. It goes around and finds all the relevant files. It updates them all in a nice way. It makes a patch for you. You can send it off to whoever is going to review it, and so on. But we've made a huge benefit in terms of predictability, since we are basically making a programming language for writing transformations. It's a deterministic programming language. It kind of just does what you tell it to do. So users in general are satisfied with the results that they get out the other side. Sometimes it's necessary to refine it. You might not have taken some issue into account. But again, also since it's very much based on the source code itself, it's easy to modify the specifications to improve them in some way. So the kind of goal, the original goal was that actually other people should be using the tool. So we can ask, did it actually work? So this is the use of Coccinelle. These are like commits in the Linux kernel that mention Coccinelle. So there are over 11,000 of them. The blue ones are made by the Coccinelle developers, so we had to do some work to actually get the idea out there in the community. And the pink ones are done by other people. You can see here it's kind of declining a bit over time in the recent years, but on the other hand, Coccinelle is in various continuous integration tools of the Linux kernel, and we're also in touch with other people who are using it for various things where they use it maybe more for exploration and for prototyping things, but the actual transformations they do are very kind of specific, and so they don't necessarily always mention Coccinelle when they have used it at some point in their development process. So in conclusion, Coccinelle is a user-friendly tool for updating C code at large scale, inspired by developer needs and expertise. Over 11,000 patches. It's been kind of growing continuously over the years. It allows developers to react quickly to changes in the code base. So if you're not using Coccinelle, the kind of standard thing to do is like make a temporary version of the new function, and then you've got a few of them updated, and then you hope that other people will take care of it over time. With Coccinelle, you can sweep over the code base and do the whole thing. And this whole work kind of follows a bit the inspiration from Jens, which is you can, it's interesting to think about things that are interesting from a programming languages point of view, but that can actually also have an impact in the real world. So everything is available, so thank you very much, and thank you, Jens, for all the discussions at various times over the years.